Welcome. Let me just look at an example of a computation in quadratic cohomology. So here is the framework. It's very general. It works for simplistic complexes. It works for delta sets, which are more general objects. And we have a nice topology in such an object with open sets and closed sets. And there are possibilities to model manifolds. If you have a manifold as your host, G, and U or K is a submanifold, we can look how this is embedded, and we want to look at invariance. Now, simplistic cohomology, the usual cohomology which Poincaré and Betti have considered already, is something which is homotopy invariant even. So it is also intrinsic for U and K. U is the open set, K is the closed set, and G is the union. So you can look at that, and it's pretty robust. For quadratic cohomology, also the interactions play a role, and then it's topological invariant. So you have to be careful with the setup. And what I want to do is eventually to look at knots, one-dimensional circles embedded in three-dimensional sphere. So this can be done in any dimension. You can look at any manifold embedded in any other manifold. And here I look at one of the simplest examples, which is a zero-dimensional sphere embedded in a two-dimensional sphere. And so as a two-dimensional sphere, I just take the icosahedron, one of my favorite spaces, and has been favorite spaces since antiquity, and it's very beautiful symmetric space. It's written here as a graph skeleton, and as the open set, I want to implement the zero-dimensional part as an open set. So I take two open stars. These are kind of from one point and another point, and this is a zero-dimensional space. If they don't overlap, you cannot take 1, 3, for example, because they are adjacent. 1, 4 is also subtle, right? When you take 1, 4, the complement, what happens with the complement is not a manifold with boundary, right? It's homotopically, this is the same situation, but what happens is topologically, this is different, because there is a one-dimensional part here, right? When you look at the connection between 6, 5 is alone. If you would take 1 and 4, you get a different cohomology, quadratic cohomology. And what I did is, for today, just take these two examples. I take one example where I take 1, 2, and I take an example where I take 1, 4. So that's this case. And we see, I mean, the simplistic cohomology is the same, but you see that what happens already, the Betti vector for K is different, and also there is interaction parts, which, by the way, I think about as geometric objects by themselves, because they are delta sets, they have a cohomology, they have a Dirac operator, they have a Laplacian, they have wave equations on it. All the theorems hold on a delta set. And so these theorems which I mentioned here hold also in this quadratic setup, which is a different differential complex, right? So if you have a different cohomology than usual, and this is also something which one considers in the continuum. If you look at the elliptic operator, elliptic complex over a space, when you study that, that's what Atiyah Singer did. It's just what in the continuum, it's 100 to 1,000 times more complicated, but it's essentially the same idea that you want to understand invariance. And in this case also, it's easy to get the curvature, what you do in any of these spaces, also in the interaction spaces, UK or UU. What you have is you just shove everything, all these energies here, you shove to the lowest dimensional part, which might not be zero-dimensional, right? But it might be a higher dimensional part. But we have this framework where we can look at the curvature, and then we have also this Poincaré polynomial encodes the Betti vectors as a function, and then we have Euler-Poincaré can be expressed using this function. It's the alternating sum of the f vectors is the alternating sum of the Betti vectors. So if you do that here, for example, you know, let's take a smaller part here. What happens is if you take 10 plus 100 is 60 plus 50. So that's for this interaction cohomology KU. Here it's something which has been known, you know, since more than 100 years, right? So what we have is 2 plus 10 is 12 minus 10 is 2. And this is maybe not so well studied, right? And usually the open set, so we have a closed set, but that's the case which already Descartes was looking at. 12 plus 20 is 32, minus 30 is equal to 2. That's this Euler. Well, there's an Euler characteristic. Here we have the Wu characteristic, but it adds up nicely, and that's actually just counting that the F vectors add up nicely is this identity here, which is just counting. You don't lose any of the pairs. You look at the pairs which are, you know, give points in K, pairs which points in U, pairs, and so this is the fusion inequality which I showed you last time, which is also on the archive now, and the code which produces this is on the archive too, or on the blog, so you can copy paste that, you can put that situation in, and you get these tables. So this is something, but already here the matrices become relatively big, right? So here we have already, around about 1,000 times 1,000 matrix, you know, to compute. And if you do a real knot, if you want to take the three sphere like our world, and you take a closed loop, and so there are hundreds of thousands of matrices which are so large that I cannot handle it yet. So, but eventually I want to understand this. I want to see that this invariance here, these numbers here, which are topological invariants, really allow you to distinguish, you know, different spaces, embeddings. Even so, the complement might be, indistinguishable topologically using the standard simplicial cohomology. So there's not only the quadratic cohomology for K, the quadratic cohomology for U, but it's also the quadratic cohomology for these interactions. Interaction between K and U, the interaction between U and U, which was a little bit a surprise that you can have an interaction of U with U, which is actually already coming in here, right? This interaction of U with U gives us actually here, this is the interaction of triangles in U with themselves, in triangles which intersect in K, and then you get here already an invariant. Actually, what happens here is this is a different situation than here, just because of that kind of neck which we have, this one-dimensional neck. But if you would take the, say barycentric refinement of that, and you would compute everything, again, you would get the same numbers here. And so that this goes to the continuum, and you have invariance for manifolds embedded in another manifold. Doesn't even have to be a manifold. Any closed set in a simplicial complex can be studied like this. That's it for today.